Thank you for joining in. This project is funded by the European Union Horizon program. Our webinar series is a part of the Circuits project and EU Green Week 2025. Please enjoy.
Good morning. My name is Antoinette van Schijk. Maras, just a brief introduction. Maras is a technical consultancy company located in the Netherlands in the field of recycling, sustainability, and circular economy. And we have both an academic and industrial background, which we link to provide a consultancy and develop tools to quantify, in fact, the end-of-life phase of products, and a bit more extended also over the other life cycle phases. Within the Circuits project, we developed the recycling simulation tool, which is a digital tool to quantify, in fact, the performance of the end-of-life phase and perform the circular and sustainable evaluation of recycling. Okay, if we speak about recycling of complex products like we have under consideration within this project, but also as we see around, recycling is in fact about unmixing the materials used and intensively linked in these products. How we can do this is on the one hand determined by the design, which determines which materials are combined, used, linked, and how they are integrated. And of course, by recycling technology, which is available to unmix these materials, to break the linkages between the materials. And that's determined both by process physics and thermodynamics. What you see here, and it might be familiar to some of you, if not, what you see here is in fact the metal wheel. We call it the metal wheel, and it's a graphical representation of the metallurgical recycling infrastructures which are presently available in industry, best available technology for the recycling of the different base metals, which you see here in the inner circle, but also for all other interlinked materials, which you see also identified in this circle. What you have to think of is, if you look at the specific section, this is a full metallurgical recycling structure. So not just one process, but a very large link of different processes, different plants, which are all available to recycle specific base metals and their related materials. If you speak about recycling, you always choose a particular recycling route for either a recyclate or a component. That recycling route determines which material you can and cannot recover, and that's in fact depicted by the green, the yellow, and the red buttons. So it's good to realize that recycling is always a trade-off between recovering the one material and sometimes losing the other material due to the link in the design, which is not always compatible with thermodynamics, which is available to separate them. So this is the legend. I will skip it, but if you want to have the slide for further reading, you can read it through. This is the basis for the model. All these processes have been modeled in the recycling simulation model in order to assess the circular economy performance of the end-of-life phase of the products we look at in this project, but also in a wider perspective. In this presentation and also within the Circuit project, we specifically focus on the metallurgical recycling routes because we look at a modular approach to recycling, which means that we do not thread and sort the small components we have under consideration, as you will lose a lot of materials in the threading and they're too small to do so. So we consider them to be dismantled from the product and to be sent to the most suitable or best available recycling option. What we can do in a model is assess different recycling routes, different recycling options for the components we have under consideration, but also look, okay, what happens if the part or the components is being dismantled into smaller parts, if we have components being dismantled or left over from the repair or whatever, which recycling route is the best to use, and what is the quantified performance in terms of different recycling KPIs. So behind this model, there are different flow sheets, different recycling infrastructures, of which you see here on the left and right hand side a couple of examples: steel processing, copper processing, the light metal processing, but also plastic and energy recovery processing. Just to give you a flavor of the size of the model, it's about 190 unit operations over all the different flow sheets, which are all interconnected in the model. We have about 900 streams, and that means that both the input, the intermediate flows, and all output flows. So we trace all materials, all components throughout the full flow sheets in a full mass, energy, and exergy balance. And if we look at the number of materials contained, compounds, it's over 300, and that are the materials flowing in from the design, but also the compounds being created due to the physical processing and thermodynamic processing of the materials, so within the metallurgical processes itself. So it's a large model. I will not run this live because the model is quite heavy to run from a computational point of view. So I will show you some screenshots to give you an impression what is behind the model. As I said, the model contains a wide range of different flow sheets. I only show a couple of them. This is, for example, the copper and lead metallurgy, the lead refining, but also the recovery of precious metals. And along with that, there are many, many more metals included in the model, as you saw in the metal wheel. It's based on industrial reality. So it's not just an academic exercise, but these processes exist in industry, and these have been models in HSC Sim. That's an industrial platform, a professional modeling platform, which is also used by my colleague, Professor Marcus Reuter, not only to model plants, but also to design plants in order to perform bank studies and also to build them in the end. So that's what is behind this recycling simulation tool. Of course, when you look at these plants, and I said it in the beginning, we combine both an academic and an industrial expertise in these models. And the models are based on physics and thermodynamics of all processes, calibrated on industrial experience. We're not using plant data for two particular reasons. There are many models which take split factors, for example. Also, if you look at threading and sorting, the model is also expanded with that part. I'm not showing that now. On the one hand, we do that not for plant confidentiality reasons, but the other reason is that every product has its unique recycling performance and its unique recycling infrastructure and fingerprints and split factors within the processes, which can only be well captured and described with physics and thermodynamics, and not when you take a fixed average rate and put that into a model. So that's the clear reason for that. What are the outputs of the model? Recycling recovery rates. This is coming directly out of the model. And then many others, which I will not show now, but like to demonstrate more in the demo we performed within this project. And I'm taking the demo for the Bosch ECU design. Bosch had some particular questions for the end-of-life assessment. Of course, the evaluation of the recycling performance, the circular performance of the product at the end of life, comparison of different designs, what kind of recycling rates can be achieved, so the provision of recycling KPIs, but also what can be used as design for recycling feedback from the recycling assessment. And also, what are the best recycling options to recycle the ECU design under consideration? And what if we look at the design itself? Is further dismantling into subcomponents beneficial in view of recycling, yes or no? And also, how can we balance repair? Because the Circuits project is also about repairing with recycling. So these were the questions by Bosch. And let me take you step by step through some of the outcomes. This is the ECU design, and if we look at recycling assessment, the first step in that is data processing. We need to make the link between the beginning of life and end of life. So that's the first step we do within the recycling simulation tool. It's making the link to the bill of materials and full material declarations as provided by the OEMs and the partners in this project, or any other partner for which we do these type of assessments and consultancy actions. The data is taken from the bill of materials, translated in what you see on the right hand side, and I'm only showing a small part for confidentiality reasons, into a full chemical composition that might look complex or too much detailed, but if we speak about recycling, it's important to know in which form the materials are present in the design. I always take the simple example of aluminum. If we have aluminum present as a metal and as a nice metal block in the design, which we can separate either by physical separation or can take out by hand and send it to the recycling, the aluminum recycling or smelting route, we can recycle aluminum quite well if it's not too much contaminated with other materials. However, if aluminum is present as aluminum oxide, either as a filler in plastic or in a capacitor or whatever, the recycling rate will be 0. So this immediately indicates why the chemical composition is needed. So that's the first step we do in recycling assessment. On the left-hand side, you see a more easy picture to understand, which is also directly linked to the metal wheel. And if we look at it and we want to decide, okay, what should we focus on in the recycling? What are the most important points to focus on recycling action on? Is we see that iron and copper is not desired in recycling. So if we want to recycle this part, we need to take apart the copper and the recycling. Otherwise, we would lose, for example, the iron to the copper slag, and copper is a high contaminant in iron processing, and so it wouldn't be possible to send this part to the steel processing. So we need to further separate this to increase recyclability. This is based on mass. If we now look at from another basis, is if we look at the exergy. I will not discuss the exergy concept in detail, but exergy takes into account, in fact, the effort to create the materials being used, but also the effort to recycle, the dissipation of energy during production, but also during recycling, and the dissipation of material quality. So what we did is, in the model I showed, there's physics and thermodynamics. We can also do an exergy balance. And if we look at the material from an exergy point of view, the focus is suddenly very different. And we see a high focus and a dominance of the organic parts. That's because the organic parts are far away from the standard state material as we find in nature. And it takes a lot of energy and exergy to produce them. So we like to maintain that. So that changes or might change the focus of recycling, and we need to maintain organics when recycling this. And then as a next step, we can also focus on the recycling of the metals, because of course, due to legislation, we also need high recycling rates. This is just to indicate that there are different ways to also look at recycling. As Bosch asked us also to provide feedback on repair action, the exergy content of the part is also saying predicting effective focus in the repair action. So we also provided the exergy values to Bosch, and they're using these values in their repair assessment. Of course, a clear outcome of recycling assessment are recycling KPIs. On the one hand, we can look at the material or the total recycling rate of the product, but also at material recycling rate. We do that at 3 different levels, which you see here on the left-hand side. If we really want to maintain circularity, we need high quality, so that's the top one, and the level 2 and 3 are the lower quality materials, and we split the recycling rate up. As I said, Bosch is also looking at dismantling. This is the total part, but we can also predict recycling rates if we have, for example, a first dismantling step or a second dismantling step. So for every stage and for every part or subpart, we can do this recycling assessment, not only looking at the total recycling rates, but also at the different materials. And here you see a selection of the materials. And if you look carefully, looking at the different dismantling steps, you will see the colors and the bullets changing in the inner circle, so it changes. And this can help by decision making. To what extent will I dismantle? Which materials do I recover? And where can I find the best balance? Not only by looking at dismantling, but also comparing different recycling options. As I said, there are two different ways to look at recycling. The standard way is mass-based. That's the basis for recycling rate calculation. That's what you see here. So all flows are modeled based on their mass for all different materials, as I showed in the beginning, which are present in the design. So we can trace every material throughout the entire flow sheet. So also predict where the losses occur, what type of emission occur, etc. We can also do that on exergy. So you see the values changing from ton per hour to exergy values. The nice thing is that we can also quantify the content of the product in exergy, terms of exergy, as I showed in the beginning, and then also look at the effort of the processes. Does it still make sense to recycle a product or a material, or to add additional recycling steps? And we do that based on the exergy efficiency. So that's a second denominator to quantify recycling performance and to perform decision making and support decision making in what recycling options are best and where should I focus recycling on, where do I stop, and where can I still find benefit. This is, of course, also related to LCA. In the HSC theme, we can directly link all the flows to LCA. So within this project, we also link LCA to the LCA as being performed by SUPSI. But we do that, if you look at the general LCA databases, recycling at end of life is always more a closing, is represented by average recycling rates. But as I said in the beginning, recycling is a unique fingerprint figure of a product, a design, or a recycling route. And this approach and these tools allows us to quantify also the LCA of the end of life for each unique design and recycling route. And we link that up and we provide that type of information also in this project to, for example, SUPSI through OpenLCA. Brings me to my last slide, just to give you an overview of the features. We link design through data processing with the digital twin of the recycling simulation of the recycling industry, predicting different KPIs, also circularity indicators, of which exergy is a very new and innovative one, which can express everything in the recycling system in one denominator. So not only having to compare mass and energy, but we can bring that all together in exergy and can also link with provide an end-of-life LCA figures. What can we do with it? System assessment, recycling flowsheet optimization, end-of-life management of products on a multi-parameter basis. We can provide design for recycling and other advisory by hotspot identification in the design. Where are the problems? We can compare different design alternative and recycling options, and of course provide KPIs. And within this project, we also link it to other external databases and platforms. Mattia presented in the beginning the Circularity platform. We can capture these models in neural net models. That's what we're busy with. We have a long-term experience since 1990s in AI in order to have a fast calculating options. So that's what we perform within the Circ-uits project also. We can link to the digital product passport, recycling passports, existing circularity indicators linked to OpenLCA, and also provide the basis for setting standards as being done, for example, in the CWA within this project. That closes off my presentation. I'd like to leave you with some references for further reading, and thank you for your attention.
Thank you for watching this webinar episode. If you're as passionate about sustainability and innovation as we are, here's how you can get involved. Stay connected with us on our social media and website for the latest updates and insights from the Circ-uits project. Whether you're an individual or an organization, there are plenty of ways to contribute. Reach out to us to learn more about partnership opportunities, events, and initiatives.